All right, so we're looking at the logarithms lesson today, but first I want to review a question from yesterday. I think it was probably the hardest question from yesterday. So if you can find at the bottom of worksheet 2B, I want to look at number 77. Okay, 77. We have number of bacteria in a colony growing exponentially, and they want to know how many bacteria were there at 7 p.m. So the most common mistake from kids is they look at the question and they think they can do some linear work. Like, oh, I'll figure out how much it's growing every hour. But that is essentially what you have to do, but it's not an easy calculation. This is exponential growth, so it's a little different. What we're going to do is we're going to pretend like time starts right here. So this is my initial value of 100 bacteria. And then 2 hours later, we have a count of 4,000 bacteria. So I don't know if you guys put 2 and 2 together yet, but this bacteria is growing at a very fast rate. So let's figure out how much it grows every hour. So we're going to start by using our simple growth and decay formula, this guy. And if I start plugging in stuff I know, like for instance, the initial value. So if I'm going to start time right here, that means my initial value of bacteria is 100. And I don't know the rate, so I'm going to leave that as a variable for now. But the only other piece of data I have is that at 4 p.m. you have 4,000 bacteria. So how much time has gone by from the start of my problem to now? 2 hours. So I'm going to plug a 2 in for t. And then the other thing that I can plug in, so I don't have too many variables, is that my final amount of bacteria after those 2 hours is 4,000. So we can do some algebra now. We can solve for the r. And I'm just going to warn you, it's a very atypical rate because it's a very fast growth. So we're going to divide both sides by 100. I'm going to need a little calculator assistance, guys, because I do want decimal answers here. Like square root of 40 is nothing I want you to have like simplify algebraic. Like I know normally I want pretty answers. Not on applications, we don't. All right, so go ahead and square root 40 for me. Tell me what you get. 6 point something. It would work better if any of you had calculators in front of you. Let's try that. Taylor, you tell me what you get, kiddo?
I guess.
Did you type it in? 6 point. Give me some more.
2, 4, 5, 5, 5.
Okay, I'll call it that. Thank you. So that one last step to solve for the rate is we're going to subtract 1 from both sides. And then this is where kids freak out because they're like, oh, well, that's not that big. They're like, oh, 5.3246 is your rate. No, that's the decimal for the rate. So the percentage is 532.46%. It's a very fast growth, but that's how bacteria works. That's why it's so disgusting.
It's disgusting.
Yeah. Even if it didn't grow fast, I'm with you. All right, so we know that the formula we can use now is that our bacteria starts off with 100 at 2 o'clock. And if I plug in this r that I just found, which I am going to keep all those decimals that Daniel is rattling off to me, because it's going to give me a more accurate answer since this is multiple choice. But question, what do we plug in for time? Because they want to know 7 p.m. So from the start of time to 7 p.m., we're talking 5 hours. Yes, please plug in 5 for t. And this is on your home screen. Type this baby in, and I think your answer comes out real close to H. But double check that for me. Maybe it's good bacteria. Maybe it's that stuff that's in your gut. It's like 1 million, right?
I hope this is good bacteria.
Well, yeah.
1.01.
That, yeah. A lot. The answer is a lot. Which we kind of knew. Had a really fast growth rate. So that's the question. It's not going to show up on your no calculator test, but it will show up on the following test. Speaking of your no calculator test, could you all look over to the board over here by Mr. Cameron? You might notice there's been some changes to the plan for the week. There's no longer a test on Friday. Okay, so the test got moved to Wednesday. Let's talk about logarithms. One of my favorite topics. All right, so yesterday we talked all about exponential growth and exponential decay. And today we're going to refresh your memories on logarithm functions. So you're on worksheet 3. And logarithms are a bit of a mystery to most kids because you really have a hard time understanding, number one, how the math of a logarithm works, and number two, like any sort of concrete usage for it. Because you're like, what exactly is a logarithm? And the answer, the best answer I can give you is it's the inverse of an exponential function. So like there's lots of things in your life that you could visually see like an exponential function being applied to. You know, growth of money, growth of bacteria. You're like, yes, that makes sense because it grows exponentially. It grows very fast after time goes on. Logarithms are the opposite of that. They grow really fast at first, and then they like flatten out, essentially. They don't totally flatten out, but they grow very slowly as time moves on. So you're thinking like, well, what does that mean? So there are applications, and they're really rooted in solving for exponentials. You need logarithms to solve exponentials because they are inverse functions to each other. So here's the big idea for today. This is our exponential growth from yesterday, right?
Yeah.
And it had a horizontal asymptote here at y equals 0. Well, this is a logarithm of the same base. Notice they are reflections of each other over the line y equals x. So while the exponential had a horizontal asymptote at y equals 0, what do you notice the logarithm has? A vertical asymptote at x equals 0. Notice how the logarithm had a y-intercept at, usually it was at 0, 1, unless there's some shifting or something happening. The exponential did. The logarithm has an x-intercept at 1, 0, unless some shifting is happening. So everything that you knew about your exponential yesterday, we have to now apply it to logarithms. Now here's the thing. Remember, your next test is no calculator, so it wouldn't even matter if you had your calculator because you can't use it. The second thing is, go ahead and graph a logarithm on your calculator. Could you please all go to y1 and type common log of x? We'll talk about why it's common log later. Just type log x for me. And then look at a logarithm in the standard window. And this is where I can tell who's a cheater pumpkin eater in Algebra 2.
Because it stops. Right?
Yeah, because they graph this. They go, oh, there's your logarithm. And I'm like, what? Did you not listen to anything I said, child? And they're like, no, I did not. So they are forgetting that their calculator is not doing a decent job at all of graphing a logarithm. The calculator doesn't have enough pixel ability to graph the rest of this tail. It comes, whoops, that was not supposed to do that. It's supposed to come down along the axes and kind of scoot along it as a vertical asymptote, but your calculator isn't able to fill in those pixels because the numbers are so incredibly small at that point, it just stops trying to graph them. Which is kind of ironic, because that's what I do too. So what I do is I go, gosh, these are awful numbers. So then I draw in with a highlighter where my vertical asymptote should be, and then I just kind of fudge it from there, which is what you're going to do too. All right? So you might be wondering, oh, Bruzo, I don't really understand logarithms. How are you going to make me do these without a calculator? We'll get to that, yes.
When you trace the logarithm,
it falls off, yeah. Because it's jumping by a certain increment. And if it's, what's happening on those x values, Daniel, it's going by a factor of 10. So the x values go from like 1 to 1/10 to 1/100th to 1/1000th to 1/10,000th, and it doesn't go that small. So it just says, I give up. So basically your steps, because of the window you're using, your steps are too big to continue graphing the function. So your graphing calculator, while it does amazing things, graphing logarithms is not one of them.
What if you change the window?
You can change the window and get more points, yeah. It's kind of irritating. Isn't it just better just to know that a logarithm scoots down? Yeah. All right, let's talk about these logarithms, guys. Your brain does not think in logarithm form at all. Logarithms are incredibly useful in algebra. They're very difficult to do mentally. So when you have a no calculator test, you're like, well, how's that going to work out? You are going to rewrite your logarithm in terms of an exponential. So this is the formula that relates logarithm form to exponential form. I'm going to rewrite it not using x's and y's because that really bothers me because usually your problem also has x's and y's in it and they're not going to be in the same spot. So if you don't mind, I'm going to rewrite it with colors, of course, using B's and A's and N's. All right, so logarithm form. They start off with the abbreviation for logarithm, which is log. And then in a little subscript position, they're going to have a little number. Usually it's a number. And we refer to that as the base of the logarithm. So it's the type of logarithm you have. Now inside of the logarithm, which you don't have to use these parentheses, but I think it really helps kids understand what's mathematically happening. Inside of the logarithm function, you are going to have something. I'm going to call it n. And this logarithm equals an answer, which I'm going to call a, because I'm a very clever lady like that. This is logarithm form. Ah, yes, clear as mud, right? Like, this doesn't mean anything to people. because your brain really only thinks of things in exponential form. So if you could translate this to exponential form, then you can start thinking about the question. So exponential form has the same base. So whatever this little number is for the basis of the logarithm, it's also going to be the base of your exponential problem. And then for me, dyslexia says you're really bad at memorizing formulas. So a trick that I had to utilize when I was a youngin' was to say, okay, as long as I can figure out who the base is, the other two numbers just switch. So in my head, I just remember that these are going to switch order now. So what becomes my exponent is what used to be my answer. And then my answer is what used to be in the logarithm. So one of the challenges for you on your no calculator test is, can you write logarithm form in exponential form, and can you write exponential form into logarithm form? Cool, because that is kind of the basis for like the next few questions on the test too. Let's see this in action, guys. On your notes, number 1, these are all in exponential form. I want you to write them, or sorry, these are all logarithm form. I want you to write them in exponential form. So the first thing I would do is I'd identify who is my base.
14.
The base is 14. Very good. So I'm going to write down a 14 to be the base of my exponential. And then I just remember the next two things are going to flip-flop, right? So the answer, which is y, now becomes the exponent. And then what used to be in the logarithm, this guy, is now my answer. That is exponential form. Now, here's what's troubling about number 1. I don't know if I'm right, because there's too many variables in this to be like, yes, clearly that is a correct representation. Like 14 to some power equals something I don't know. Okay, cool. Let's look at number 2, though. This one is self-checking because it's numeric. So who's your base? 17. Good. So this guy is my base. He's going to become my base here as well. And then I just do a little flip-flop here. So the 2 becomes my exponent. And then what was in the logarithm, this 289, is now my answer. And that's totally right, because 17 to the second power is 289. Okay, so this is something that we could figure out in our brains. Logarithms, I don't know. The only way I can figure it out is either to have a chart of logarithms or to rewrite it as an exponential. Okay, so you guys are going to be forced to rewrite it. So I really like going from log to exponential form because my brain can really wrap around that. I hate going exponential to log form. My brain does not understand it, so I just kind of suffer through it. So the first thing I have to remember when I'm writing in log form is that I have to write down the abbreviation for log. So I write down log, and then I have to identify who my base is. Who is the base in this question? Yes, bases hold things up. So A is your base, which means he's also the base of your logarithm. You don't have to have parentheses here, guys. I just really like when there's parentheses around the logarithms inside, because some kids don't understand that the logarithm is a function. You're applying it to a value or a variable. So the parentheses really indicate that. Who goes inside of the logarithm, though? Yeah. And then what is my answer to this logarithm question? Yeah. And again, you're writing this and you're just hoping that you did it right, because this is very awkward for your brain. A logarithm is a function, like sine and cosine are functions. Yeah. So you're applying it to a numeric value, or many numeric values in some cases. Like how this.
What does the function look like if it wasn't abbreviated?
It's called a logarithm. And if you do a logarithm of any base, you would apply it to a variable in order to graph it. Just like how, you apply the square root function to a variable.
Yeah, I was just curious, like, because earlier you said, like, the abbreviation.
So instead of writing out, it's just like we have symbols in math to indicate things that we don't want to write out. So instead of writing logarithmic function of base 3, we write log 3. Okay. So number 4, same idea. I know I have to write down logarithm, the abbreviation for logarithm. Who is the base?
7.
Yep, 7's doing the holding. So log base 7. And then in the logarithm, we got 1 over 343.
Oh, it is. I didn't know.
And then the answer to your logarithm is who used to be your exponent. And this is a numeric one that you can check in this version. What happens when you raise 7 to the -3rd power?
You get 343 and it flips.
And why does it flip?
Because
The negative exponent. Okay, those are the type of things we got to look at next. Can you come up with those without any calculator help? Goodness, I hope so. All right, there's some properties out there on your notes that are going to help you out a little bit. I think they're right here. These are useful properties that they kind of throw at you in Algebra 2, and some of them really resonate with you and some of them don't. But let's talk about why they should resonate with you. Log base b of 1 is always equal to 0. That's my answer to that too. Like, all right, I don't think like logarithms. This bothers me. But what if I rewrote it in exponential form? B to the 0 power equals 1. Yeah, because anything to the 0 power is 1. So that makes lots of sense, right? So this guy, b to the first power, is just going to give you b. Yeah, that's absolutely right. So that makes a lot more sense, right? This one says b to the x power equals b to the x power. Yeah.
So why would the extra like?
You'll see them in a minute. You'll see these properties in use. Okay, now this one's a little hard for kids to understand because they're like, wait, what's happening here? Okay, when you have base b and up in his exponent position, you have a logarithm of a matching base. These cancel each other out. Remember this property? And then since there's nothing holding the x up anymore, it just drops back down to the regular level and the answer comes out to x. So when you have an exponential with an exponent of a matching base logarithm. So b raised to log base b. So we really like to use exponentials and logarithms to undo each other, quote unquote, in math. And that's exactly why we have to learn about them. Yes?
If it was
Different.
e to the power of log base c.
That would not cancel. So you'd either have to rewrite b as a c or c as a b in order to use that property. We're going to see that coming up next. Good foreshadowing, Daniel. All right. Remember, your next summative is no calculator. And guys, I mean no calculator. Like not even a scientific one. So I will give you a chart. So if you're like, man, I don't know what 5 to the second power is, I'll give you a chart. But I feel like you secretly need it. Or know it. You don't need it. But it's like a little binky for you. So it's fine. All right. So here, I want to know what this equals. Your brain does not think like logarithms. So you got to rewrite this. Who's my base? Okay. Oops. Why am I using the wrong colors again? There we go. 5. And then it's raised to some mystery power. And you're supposed to come out to an answer of 1 over 25. Anyone have any thoughts on that? It is -2. Walk me through your thought process there, Daniel. Why is it negative? Let's start there.
Okay, well it's negative because it's flipped. It's in a fraction.
Okay. In order to create a fraction, you would have to use a negative exponent. Cool. And then to change it from a 5 to a 25, you'd have to apply the squared power. Very good. Yep. All right, this one. Same idea. I want to know what this equals, but my brain does not think like a logarithm, so I'm just going to rewrite this. So 3 raised to what mystery power is going to give you the square root of 3? Well, in order to answer that one, you'd have to have knowledge of another way of saying square root as a power. And I'm hearing from Daniel that the answer is 1/2. Isn't the 1/2 power the same thing as the square root?
Yeah.
Yes. That's a bit of a tricky question, yeah. So I just want to make sure we're all crystal clear. I have a lot of kids who made their way through Algebra 2 and Honors Algebra 2 doing these on their calculator. You will not have a calculator. Got me? That's
But
okay.
you're not going to throw us some like, I want to kill myself.
No, but you took that very dark.
I'm sorry. I've gotten those questions before. They're terrible.
I'm sorry. I didn't mean to do that. Okay, so here, we can approach this one of two ways. My friends who really love properties see something that happens right away. Who is this, by the way?
That's a natural law.
Okay, thank you. Now, my friends who had me for Algebra 2, I got lots of stories about natural logarithms. Okay, first of all, you'll notice that I write them in cursive. Because what do Algebra 2 kids tell me that is?
In.
Yes, they say, what's in? And then I want to, like, scream. Like, we've been talking about the natural log for a week, and then in the middle of the test, they're like, what's in? What's IN? Or they write capital IN on their paper, and I'm like, ooh.
Or just let them think it's IN, as long as they know that it means.
No, because I can't do that. I can't let them go on in life thinking that's in. Okay, so it's natural log. So, like most humans, Americans, let's say Americans, they're like, why is natural log ln? Because we think the world revolves around us, right? Yeah, we're pretty sure it's something to do with the derivation of it back in some other country. I think it was France. I think the French are accredited for the development of the natural logarithm. So you might be asking yourself, well, what is a natural logarithm? Well, it's a logarithm that is actually in nature quite a bit. His base is e, who's called the natural number. So it's a logarithm of base 2.718 blah, 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 which is the number e from yesterday. Either way, the natural logarithm is my favorite logarithm. In math, it's my favorite because it's so nice and pretty to write. I get to use my cursive L and N. It's 2 letters instead of 3, so it's better. So much easier to write. And then short story. I know Algebra 2 kids already heard this one. Taylor's already laughing. So Mr. Abruzzo was writing like thank you notes after Christmas or something one year, and he's signing like our names. He's like, Merry Christmas, love, Aaron, Ryan, Nat, and Log, because my kids are Natalie and Logan. And we call Nat, and we call Logan Log. And he was writing like after the 13th letter, he just like drops his pen and he's like, I cannot believe you. And I'm like, what? And he goes, you did not. And I was like, what? Because that's very accusing, that statement, right? And he's like, you are such a nerd. And I said, I know, and I'm not disagreeing with you. I just, what? What did I do? And he goes, you named your children natural logarithm. I did. But I didn't. It was like subconscious.
It was you two together, right?
I didn't even name the kids.
Yeah, exactly.
I blame him.
So,
So my kids will answer to natural logarithm in public.
like, so if you say natural logarithm, they'll both come with it? Or
Yes, mother. No, they like former students have referred to them as it's natural logarithm, and my daughter like hates it. She hates it. She thinks it's so stupid, and my son thinks it's great. So they will answer to it. My daughter is 9, so she doesn't really like anything I do, but she really didn't like that. Okay, anywho, natural logarithm. What is natural logarithm of base again? Okay, so I get this from kids a lot. They write this, natural logarithm base e of x. Guys, I don't want to ever see you writing that ever again. That is wrong, 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 wrong. Natural logarithm is a logarithm base e. So you can write log base e of x, or you can write natural log of x. You cannot combine natural log abbreviation with an e. That's complete gibberish. We're not picky about that in Algebra 2, but we are picky about it in PreCalc, okay? Because you're going off to college, and we don't want you being fun of in the future. That's all. I'm not going to college. I'm dropping out today. All right, so natural log of e to the 7th power, Those of you who remember the formula that we were talking about earlier, if you have a logarithm who has a matching base, these just cancel each other out.
So now we have 7.
So the 7 drops down, and the answer is 7. Yes, absolutely. So if you didn't like that canceling formula, or you were in a jam and you couldn't remember it, let me rewrite this problem real quick. Natural log of e to the 7th is log base. Yes.
You don't need to know that canceling formula.
Yeah.
Inverse.
Yeah, I gotcha. Well, that's why the canceling formula works. But let me show you for a minute. This is what's going on here, guys. Log base e of e to the 7th power is what you're looking at, right? And they want to know what this equals. So basically it says e to what power equals e to the 7? 7. Right? So it's like a really stupid question once you look at it in exponential form. And that's why a lot of kids just go, oh, I like that canceling formula way better because I know it's going to be stupid in a minute, so let's just understand that they cancel. So part D here, I think we all want to take the shortcut, guys. E raised up to a logarithm who also happens to be base e. These are just going to cancel each other out. And the 5 drops down. The answer to this question is 5. What kind of a logarithm is that?
Logarithm.
This is called, and I think I skipped a slide, so my bad. This is called a common logarithm. So common logarithms are logarithms who are base 10. So instead of having to write like log base 10 of x every time, since they used it a lot, they just started calling it the common logarithm, and they just write log.
I do have a question.
Yes.
Something I never got good at or understood. Was actually like typing in logarithms. It's like, how does the base go?
So the
I know
button,
we're not using calculators.
I gotcha. The button on the calculator that says just log,
Yeah.
that is the common logarithm.
Okay.
The natural log is logarithm base e. Those are the only two quick keys you have on your keypad.
Okay.
So if you wanted to use like log base 7, there's ways to get around that. You either have to change the base using one of the options, or change it using common and natural log change of base formula, which we'll go through all of that next week. But the quick keys on your keypad are common and natural. Yeah. And why would one assume that base 10 is the common logarithm? Why would they keep resorting to base 10?
10's a nice number.
10 is a nice number. 10's the greatest number of them all.
7's pretty good.
Isn't all of your math in base 10? Yeah.
It is.
Yeah. It's all base 10, guys. So that's why they refer to that as the common logarithm. Oh, I skipped that problem, though. So now that we know that this is a common logarithm, which secretly has a 10 in here, what happens with 10 raised to the log base 10? They cancel, and the 13 drops down. The answer is 13. Those are my favorite questions. They're the best. All right, practice this with me. No calculator, please. So log base 7 of 7. There is secretly a power right here. What is it? There's secretly a 1. 7 to the first, also known as 7. So these cancel. The 1 drops down. The answer is 1. Now, those of you who don't like this canceling formula, maybe you rewrote it as 7 to what power equals 7? And then you thought really hard about it for a minute, and you said the answer is 1. Okay, so here, what kind of a logarithm base do you have? There's secretly a 10 here, so if you like to write the 10, go ahead. 10 to the log base 10 knocks out, the 5x drops down. Your answer is 5x. Oh, boom, they're gone. The 2 drops down. And then it's got to be a little trickier than this in PreCalc, right? So let's give you something weird. Okay, this one. You can rewrite 36 so it matches. This is what Daniel and I were talking about a minute ago. This property only works out if the 6's match. Can you rewrite 36 as a 6? 6 to the second power. Good. So if you rewrote it like that, these knock out and the 2 drops down. Now, those of you who are like, that was a lot of thinking, remember, people, I don't have a calculator. So look at it this way. 6 to what mystery power gives you a 36? Yeah, so either way, you're approaching the same problem. You're technically approaching it with the same mentality. It's just one requires you to rewrite and one requires you just to think. Okay, 5 is a bit of a thinker. So if you're just rewriting it, it's 3 to what power equals 1 over 81 without a calculator. But you will have a chart. Now the other option is you can rewrite 1 over 81 as a 3. Anybody thought about what power you could raise that to? That'll create a 1 over 81. A negative 4, yes. 4 will take it to an 81, and then the negative will flip it around. So either approach you guys take, you get an answer of, you got it. And then 6 feels like it doesn't belong on this slide because it's super easy. E raised to the natural logarithm, those will cancel each other out. The x squared just drops down. How boring. Let's talk about money. Financial literacy. So Ms. De Silva has $3,000 to invest, and she would like to invest it in an account that compounds continuously at 6%. So they've given you a formula right here. It starts off with the natural log of A. So I don't know if you guys recognize this, and maybe tomorrow, like next week will be a better time to look at this, but what they did is they took your PERT formula and they solved for some other part of it, the RT part, which they had to use natural logarithms to solve for PERT because it has a base E. We'll talk about that next week, okay? Either way, you got a formula. A is the current balance. So for this question, as I keep reading, they initially invested $3,000, and at the end of the problem, they have $6,000. So there's your current balance. The initial investment is P. That's this guy. So original principal is P. And then keep reading. R is rate, of course, and T is time. And the question they have for me is, how long will it take? So T is going to be a variable. I don't know it. It's going to stay as a variable. Here we go. What's this in thing, Mrs. Abruzzo? All right, natural log of A, which we decided was, I forgot, 6,000. Minus the natural log of your initial principal, which is 3,000. and it equals r times t. Now, I think they did tell you rate somewhere in here, 6%. So write that as a decimal, 0.06, and then we don't know t. So if I think about, okay, I'm trying to solve for t, essentially all you got to do is type this thing in, either use parentheses or hit enter, and then divide it by 0.06. So go ahead and type that in for me. And remember, you're solving for how many years you should leave money in a bank account. So if you get a really weird answer, you need to think about that. Watch that you're closing your natural logarithm functions after each one.
That's not a very good answer.
What is it?
It's 11 and a half years.
That's okay. I was hoping you wouldn't get a bad answer. But sometimes kids do this problem and they get like something really ridiculous. No, like 0.012 years. And I'm like, do you think you doubled your money in
3 days?
Yeah. They're like, yes, Mrs. Abruzzo, I think that's how the math worked out. And I'm like, oh, cool. I got no thoughts for you. All right, can you turn over to the back? Let's talk about graphing. So we already discovered today that my calculator does an awful job of graphing logarithms, which is rare. Usually it graphs really stinking well, not logarithms. So we've already discussed how my brain doesn't think very well in logarithms, and my calculator doesn't think well in logarithms. So that puts you guys in kind of a pickle for graphing logarithms. Okay.
Then why don't we just get rid of logarithms?
They're very useful. They're the thing you need in order to solve exponentials. So you need them. Because not every exponential is intuitive. Like 3 to what power gives you 20? See? Gotcha there. You need a logarithm.
With enough time, I can figure it out.
With a logarithm.
With enough time, I can figure it out.
With a logarithm. Well, then you're using a calculator, and guess what your calculators use? A logarithm. You need a logarithm.
I can do it on paper, though.
Oh, good luck.
It would
Okay.
take a lot longer, but I could.
Child. Okay, so here's what we're going to do, guys. Your brain doesn't think in logarithms. You can't use a calculator anyways. How are you possibly going to graph for me log base 6 of x? And here's the trick. You are not going to graph log base 6. What you're going to do is you're going to pretend that you're trying to graph his inverse, which is 6 to the x power. Okay, so I know they've already done this for you, but help me out for a minute. Because remember, we won't have a calculator. So I'm going to pretend that we're graphing 6 to the x power, just like yesterday. So I'm going to throw in some values. Unfortunately, many of them are disgusting. So like, I might try -2, -1, 0, 1, and 2. They are icky. Some of them. So if I'm plugging in -2 here, 6 to the -2 power is a 1 over 36. That's incredibly tiny. And then 6 to the -1st power is 1/6. 6 to the 0 power is 1. 6 to the 1 is 6, and 6 to the 2 is 36. So now we're in another bit of a jam because, remember, I don't even want to graph this. What do I want to graph? Yes, I want to graph the inverse.
So
You just flip the points around. Yeah, you just take all these XY ordered pairs and you just flip. So the first thing I'd ask you to graph is 36, 2. Are you seeing any problems here? It's like way over here, so I can't graph that. And then I'd ask you to graph 6, 1. Well, that one I could actually graph. It's apparently right there. And then I'd ask you to graph 1, 0. Cool. Oops, it's halvesies. Sorry. And then I'd ask you to graph 1/6, -1. And then I'd ask you to graph 1/36, -2. So are you guys realizing why your calculator gives up on graphing this? Because I'm about to give up on graphing it too. So what you guys are going to do is you're going to plot what you possibly can, which isn't going to be much. And then you're going to use a highlighter of some sort and kind of mark off the vertical asymptote as a guiding line. And then just from memory, you're going to have to realize that that tail swoops down and goes forever down to -infinity. Okay? Not through the asymptote, but along it. So the one on your test on next Wednesday, the no calculator test, is going to be something very much like number 9. I'm going to ask you to graph logarithm base 3. And you're going to say, Abruzzo, I can't graph logarithm base 3, but I could pretend that I'm graphing 3 to the x. That would be his inverse. So, give me some x values that you wouldn't mind using here on this 3 to the x power. Negative as well. Yeah, let's go negative 2. Let's stick with negative 2, negative 1, 0, 1, 2. Those are always safe. And if we plug these in, again, without a calculator, you're going to get, let's see, 1/9 gross, and then 1/3, and then 1, and then 3, and then 9. And then you got to remind yourself, this is not actually what I want to graph. What do you want to graph? Yeah, so you take all these ordered pairs, and you graph the reverse, or the inverse. So, 6 to the x. The previous one, are you saying?
No.
Oh,
I'm saying like that's the inverse of the log.
Yes. So this table is representative of 3 to the x power, and I want to graph his inverse, which is log base 3. So I'm going to plot a point at 9, 2. Unfortunately, it's going to kind of fall off the graph here. And then I hate when your book does this. They count the horizontal axes by ones, and they count the vertical axes by halves. I hate when I do that, but they did it. And then we're going to graph 3, 1. Again, watch the counting. And then we're going to graph 1, 0. And then you're going to try to graph 1/3 comma negative 1. Sure thing. And then I'm totally going to graph 1/9 negative 2. And it's pretty much at 0 at this point. So here's what I have to remember. That I have a vertical asymptote at x equals 0. Oh boy. And then I have to remember that this logarithm has this type of a shape. And you know what? That's pretty decent. Larger. You know, that's called the big dot theorem. I just made that up. No, I didn't. That's actually what Mrs. Hoffbauer and Mrs. Falzone before her used to call that. If you missed your dot, you just made it really big. Yeah. It's a trademark. All right, so that's what the one on your test is going to look like. But there's some on your homework coming up where then I'm going to ask you to transform this graph. This is a hoot, guys. Watch this. What happens when I take that same logarithm and I perform this transformation? What does this transformation do? Oh boy. It's a reflection over the x-axis. So essentially what it does, guys, is it negates your y. So if it was at up 1, now it's at negative 1. But then, talk to me about this guy. What does this do? X minus 2 inside of a function like this? Yes, right 2. So it's going to take all your x values and you're going to add 2 to them. All right, I don't want to write it that way, though. That was silly. Okay, so watch what's going to happen. I am not going to graph all of these points separately because some of them were atrocious. Let's do some nice ones. So if I took the point 1, 0 and I reflected it over the x-axis, I'm still at 1, 0. But then if I shifted it up 2, I'm going to be here. So I'm going to, I forgot what I was just doing. Oh, up 2, excuse me. Counting by halvesies. Gosh, I hate this. Oh, it's not up 2, though. Guys, why are you letting me do this?
I don't know. It's kind of entertaining.
Oh my gosh. Okay, I was at 1, 0. I reflected it. Nothing happened. I'm supposed to shift it right to. There we go. This guy, which used to be at 3, 1, if I reflect it, it ends up down here at 3, negative 1. And then shift everything right to. Now I'm over here. And I'm really not going to be able to graph much of anything else as far as points go, but something I could graph. What about the asymptote? It used to be at 0. And now it's at 2. Yeah, I hate how they do the axes. I hate when they... It doesn't bother me that they go by halvesies. I just wish they do it on all the axes. Really bothers me.
On all the axes.
Halvesies on all your axes. Yes. Start a chant. Sorry, publisher of the book. I just don't like it. All right. I will not make you do that without a calculator, but it does show up on your homework. Hey, speaking of homework, we got some cool application questions I skipped. My bad. Your homework, it looks like a really long assignment, but so many of them are just those quick, like, hey, 3 to what power is 27? Like, it's those questions, okay? So you're supposed to be practicing without a calculator for that section because you're getting ready for your test, right? Right. Try graphing without a calculator when possible. That would be helpful, too.